Okay, so in this video, we will tackle the subject of logarithmic differentiation. And the idea is the following. Some functions may be really hard to differentiate directly, or just plain impossible. And surprisingly, with the help of logarithmic functions, namely, we will only ever use ln, so the logarithmic function base e, because quite simply it has the simplest derivative. Remember that the derivative of ln of x, the logarithmic function base e, is just 1 over x. We could use in our next examples any other logarithmic function, but as ln of x provides the simplest derivative, it is more natural to use ln of x and not other bases for the logarithm. Let's start with a few simple examples. Sorry about that, where we can differentiate the function directly. And then we'll throw a bit of a curveball. What if I ask you for the derivative of the power function x squared? Well, this is the simple power rule. The derivative of x squared is 2x. And we're done. So if you raise x to a fixed constant, the derivative is easily found with the power rule. What if we now flip the role of 2 and x? And what if we ask for the derivative of now the exponential function 2 to the x? So now, the difference from here to here is the following. When you have a power function, it is a variable raised to a constant function. An exponential is the opposite. It is a constant raised to a variable. And if you remember, the derivative of any exponential function is the function itself times the ln, the natural logarithm, of the base. The base here is 2, so it's 2 to the x times ln of 2. What if we have the following example? What if we ask for the derivative?
Let's take a look at an example of a problem in which we're going to use logarithmic differentiation to find the derivative of the expression. So remember, with logarithmic differentiation, we're going to use the laws of logarithms to first expand the given expression, and then we employ implicit differentiation to actually find the derivative. So let's start by taking the natural log of both sides. There is a reason we use the natural log as opposed to the regular log in some other base. So we would have the natural log of y on the left. Now on the right, when we take the natural log of that quotient, remember it's going to be the natural log of the numerator minus the natural log of the denominator. And that's according to the laws of logarithms. Now I'm going to rewrite that square root as an expression, the x squared plus 1 raised to the 1/2. Now we can use the laws of logarithms again on the right side. Remember that each of those exponents can pop to the front. So now we're there, and we can use implicit differentiation to now do the derivative. Now this is why we use natural log, because the derivative of natural log is simply 1 over the expression times the derivative of the expression. It's a nice, easy rule to use. So the derivative of natural log of y on the left would be 1 over y times dy dx. Remember, with implicit differentiation, you're taking the derivative with respect to x. So anytime you have a derivative of a y term, remember that we insert dy dx to denote that we are taking the derivative with respect to x. Now on the right side, everything's in terms of x. So really it would be dx dx that we'd be multiplying by, but that of course is 1. So derivative of 2 times the natural log of the quantity x minus 2, we keep the 2 as the coefficient, and it's 1 over x minus 2 minus, now we have the 1/2. Now for the derivative of natural log of x squared plus 1, that's going to require the chain rule. So we would have 1 over x squared plus 1, but then we need to multiply by the inside derivative, which simply would be 2x. So we can start simplifying on that right side of the equal sign. You'll notice that the 2's over here cancel out, so we can just simply condense this a little bit. Now for our final step, remember that we're trying to solve for dy dx. That denotes our derivative. So what we'll need to do is multiply both sides by y, so that we have dy dx by itself on the left. So that gives us dy dx equals y times 2 over x minus 2 minus x over x squared plus 1. It's perfectly acceptable to leave our answer like that. Remember that with implicit differentiation, we often had both x's and y's in our answer. Another option, and you will see this sometimes as well, is to substitute in place of this y the expression you were given at the very beginning for y, which in this case was x minus 2, that quantity squared, over the square root of x squared plus 1. Really, either way is fine. Sometimes you'll see it one way, sometimes you'll see it another way. You could even, if you were to make the substitution, keep going and maybe distribute over the big parenthesis quantity and maybe simplify a little bit more, but it's not really necessary. So it would be perfectly fine to stop at that first line where you see the answer as y times the quantity 2 over x minus 2 minus x over x squared plus 1.
So this will be quite a lot of work directly. Let's now use properties of logarithmic functions, specifically ln, to simplify the expression and then differentiate using implicit differentiation. So here, as before, we want to find dy over dx. But remember here, and in this case we'll use all three properties. We want the derivative. So let's take ln on both sides and then simplify the expression. So we have ln of y will equal the ln of this expression. But think of it, this is the ln of a times b divided by c. So imagine that you have this ln of a times b over c. Well, properties of logarithmic function, this will be ln of a plus ln of b. C is on the bottom, so it will be minus ln of c. So we'll have here, ln of y will be the ln of this, plus the ln of this, minus the ln of this, but each time, you see, we have an exponent on the expression. Right here, this is just x plus 2 to the 1/2 power. And remember now the other property of the ln function, ln of, say, a to the b, that's just b ln of a. So now when you take the ln of this, simplify in just one go. Ln of a, b over c will be ln of a plus ln of b minus ln of c. So it would be the ln of this term. But we can move the exponent outside. So the ln of this will just be 8 ln of x squared plus 3. And that's it. Plus the ln of b, the ln of the second term. Once again, we have an exponent on the argument. We can move the exponent outside the ln. And so the ln of this will be 9 ln of 6x minus 1. Finally, this is on the bottom, so it will be minus the ln of this term, which is x plus 1 to the power of 1/2. Once again, move the power outside the ln, so the ln of this will be 1/2 the ln of x plus 2. And now that we have simplified, we can differentiate. And believe me, that differentiating these two expressions will be a lot simpler than differentiating this expression. So let's do this. Both sides again, y is this function of x. Both sides are equal as functions of x. So we can once again differentiate using implicit differentiation. Differentiate both sides with respect to x. The derivative of ln is 1 over what's inside, so 1 over y. Chain rule times the derivative of the inside, which is dy over dx. And that's equal to 8 is a constant multiple, so it just stays there, times the derivative of ln, which is 1 over what's inside, so 1 over x squared plus 3, chain rule, times the derivative of the leftover function. The derivative of x squared plus 3 is simply 2x. And we keep going, plus 9 is a constant multiple, so it stays there. The derivative of ln is 1 over what's inside. Chain rule times the derivative of 6x minus 1, which is 6. Minus 1/2 is a constant multiple, it just stays there, times the derivative of ln, which is 1 over the argument, x plus 2, times, by the chain rule, the derivative of x plus 2, but that's just equal to 1. And we're done differentiation. So, as before, on the left we have 1 over y dy over dx equals this. If you want to solve for dy over dx, therefore the derivative of this function, multiply both sides by y, so y over y is 1, y here, and now we can write our final answer by cleaning up these fractions a little bit. So the derivative, dy over dx, the derivative of this function happens to be 8 times 2x, that's 16x, so 16 x over x squared plus 3, plus 9 times 6 is 54, so plus 54 over 6x minus 1, minus 1 on top, so minus 1, over 2 times x plus 2. And don't forget the leftover y. And as always, if we can, we want to leave y or replace y by a function of x. This is not always possible, but here it is. Y was this lovely function of x. So x squared plus 3 to the 8th power times 6x minus 1 to the 9th power all over the square root of x plus 2. And there you have it. The derivative of this function is this function. It's kind of a monster, but if you look at every step along the way, the first step wasn't too hard. We simplified the ln of both sides using the properties of logarithmic functions. And once this was simple enough, then we differentiated. This was actually very straightforward. And then we just isolate our dy over dx. Let's do one more example that will involve, right from the get-go, implicit differentiation, where the answer will, in the end, be a function of x and y.